Welcome and thank you guys so much for logging on to the Scripps Technical Forum. My name is Vanessa Scott and I work in industry relations and innovation here at Scripps. And I will be your moderator / host today. Douglas Alden, who is the chair of the Scripps Technical Forum and a lead engineer for the Center for Western Weather and Water Extremes, usually hosts and moderates, but he is out in the field today. So I am standing in. We encourage this to you guys to ask questions. We want this to be a very interactive discussion and get kind of deep into the technical questions. So please feel free to enter your questions throughout the presentation, either through the Q&A button at the bottom center of your screen or through the chat. And then we will hold them till after Greg gives his presentation, and I will go ahead and moderate. And if any of you have pre-submitted questions through the registration process, if you could re-enter them in the chat, that would be super helpful too. This session will be recorded and it will be available afterwards on our Scripps Technical Forum playlist on our YouTube channel and also on the new Scripps Technical Forum website, which I will drop into the chat. We always welcome your feedback and suggestions on future topics and speakers that you would like to hear from. So please feel free to reach out to myself or Douglas Alden. I see Gwen still on there and she's no longer here, so we'll have to update that with any future ideas. So with that, I am very pleased to introduce the company and speaker today. We're going to be hearing from Seabird Scientific. And Greg Ikeda is going to be telling us how multiparameter CTDs can help characterize events like Hurricane Matthew.
All right, thanks, Vanessa.
Mm-hmm.
Okay, I'm going to share my screen here. Let's see. Okay, Vanessa, can you confirm that you can see the presentation?
Great. Looks great.
Okay, awesome. Hi, everybody. Happy Friday. Thanks for joining us today. My name is Greg Ikeda. I'm here with Seabird Scientific. And today I'll be talking to you about multi-parameter sensors and systems and how measuring multiple different parameters, maybe with a single instrument or with a single system, can get you more than just more data. There's a lot of useful information you can glean from these things. I'm going to cover this with a couple of scientific case studies and some technical troubleshooting methods you can do. Little background on me. So I have a Bachelor's of Science in Oceanography from the University of Washington. I studied chemical oceanography. After school, I spent some time as a field technician, wading out in waders into rivers, estuaries, everything, and spending some time on research vessels. Actually, we spent about 40 days on the Melville before it was decommissioned. That was really great experience for me as somebody who had recently graduated from school. I've been at Seabird Scientific for about 6 years, actually, I think more like 7 years now. And I've used Seabird Scientific CTDs for a long time. And I have over 150 days at sea logged so far. I started at Seabird in technical support and still do a lot of that stuff these days. I love working with our instruments. I love working with our customers and the scientists. And there's a lot of really interesting things that you can do with this equipment. And I just love working with it. I love answering people's questions. I love learning more about it. Currently, I'm the Senior Content Development Manager on Seabird Scientific's marketing team. So I'm making marketing content, but I'm also acting as a field scientist, getting out there, getting us data for R&D experiments, which ultimately turns into new products and new marketing content. So that's me. And so to start, I'd like to define what I mean by multi-parameter CTDs and systems. So these really encompass anything that measures multiple parameters, ideally in the same location and at the same time. Simultaneous measurements ensure that every sensor you have on your system is characterizing the same parcel of water and allows you to truly relate different types of data to one another. So we'll go over some examples, but the image on the right showcases several products from Seabird Scientific and the primary measurands that our products can cover. And while a lot of these are designed to measure just a single parameter, we have things like our optical sensors that might measure just chlorophyll fluorescence, or a dissolved oxygen sensor that measures only dissolved oxygen. A lot of these can be considered multi-parameter instruments because they either support several different instruments on them. You might have temperature, conductivity, pressure, dissolved oxygen, chlorophyll built into a single instrument and fully integrated, or you have the option to integrate and customize your sensor package to have some pretty diverse sensor types. Overall, Seabird Scientific instruments, we can combine biological, chemical, and physical measurements to get a really complete picture of your area of study. And so maybe the most prolific example of a multi-parameter system is the CTD. These are everywhere. These are a great example of the power of measuring multiple parameters. With temperature, conductivity, and pressure, CTP, you can derive all sorts of physical parameters from a given sample of water. So you can get density, specific volume, sound velocity, even salinity itself is actually a calculation of temperature and conductivity. And so if you have just a temperature sensor, you're getting temperature, and that's valuable. If you have just a conductivity, you're getting conductivity, and that's value. But when you have temperature and conductivity, suddenly you can get 20 plus measurands through the calculations you can do with those measurements. CTDs are a great example of multi-parameter systems. On top of that, most CTDs, they have the ability to integrate auxiliary sensors. This is sometimes an overlooked feature of Seabird CTDs, but in many cases, they're acting as an integration platform. The 9+ CTD we see here on the right is pretty ubiquitous on research vessels and is often the point of contact for the majority of auxiliary sensors. You might have your dissolved oxygen sensor, that's pretty common, optical sensors, pH sensors, you'll have an array of water sampling bottles, and really anything that we can cook up can really be connected to the 9+ CTD in some way. And that's really augmenting the data that we're getting from that conductivity, temperature, and pressure, and can really tell you a lot more about your area of study. Again, you can derive all of these parameters from just your CTD data, add pH to that, add dissolved oxygen to that, and you can do a lot of really interesting analysis. Beyond sort of your typical CTD package, we have what we might consider integrated sensor packages. So unlike the 9+ CTD that we just saw, where you can sort of plug auxiliary sensors in and really customize your package, when I say an integrated sensor package, I'm really talking about an instrument that's fully integrated in a way to obtain simultaneous measurements. So I'll talk more about the HydroCAT-EP V2 shortly, but this is a comprehensive integrated sensor package. You might consider something like the BGC Argo floats to be an integrated sensor package, where your dissolved oxygen, CTD, pH is all kind of built into one single package. You don't have a bunch of cables running into different connectors for customization. And finally, we have systems. These are buoys, data loggers, real-time systems. These are pretty powerful platforms that can support lots of different sensors, and they really give you high amounts of customization. And so one thing to note is that these are often collecting different types of data, but maybe at different depths. And that's great. You know, we get a deeper understanding of the water column, everything that's going on at different points in the water column, but we may not be getting the simultaneous measurements that we would get from an integrated sensor package. For example, if you're measuring pH on the surface, just below the hull of your buoy, tying that to trends in dissolved oxygen from a DO sensor on the seafloor might not be fully applicable. You'd really want to be looking at pH and dissolved oxygen measured ideally by the same sensor in the same location at the same time to really compare the trends between the two. Nonetheless, we can get tons of data from these things. And depending on how you customize your buoy system, you can really get some interesting analysis. So my point here is that when you have a multi-parameter system, you're really measuring more than the sum of its parts. Measuring temperature gives you that one parameter. Measuring conductivity gives you that one parameter. But as we saw, if you have both, you can calculate 20 different parameters. Furthermore, when those parameters are related to one another, you have a greater context into what's going on in your environment. So the data set that we have here on the right is from a spot that is subject to eutrophication in the summertime. And so we could see that from July through November, we have some pretty significant spikes in chlorophyll fluorescence. And then if you look at that, you also see these points of hypoxia with oxygen, where it's dropping to near zero at times. On top of that, if you look closely at pH, you'll see greater variance really around the times of eutrophication. And so if we were only measuring dissolved oxygen here, and you're just looking at, say, this period between September and October, you're seeing, hey, our oxygen is dropping to near zero here. What's going on here? You know that you have this kind of hypoxic period, maybe some events going on, but you don't necessarily have the answer to why this is happening. But if you add chlorophyll fluorescence into there and you take a look at the water, then you might say, okay, we are having some algal blooms here. If you add nitrate or phosphate nutrient measures to that, you could see, okay, we are getting a lot of runoff here, which is causing these algal blooms, which is depleting the oxygen in our system. And so the more parameters you add, especially if they are related to each other in some way, you can really better understand what's going on in a way that's more than if we are just measuring nutrients or if we are just measuring dissolved oxygen. And so we have systems out there that can really measure all of these things and are built to provide these kind of information with interrelated parameters. So from a scientific monitoring and regulatory perspective, this kind of analysis can be extremely helpful. If we gather all the necessary clues to a given problem with sensors, with data, we can hopefully provide a more complete explanation for a given problem or environmental phenomenon. So a really great example that we have of this is one of our science staff here at Seabird showed exactly how to use several different parameters to characterize an algal bloom that occurred in the St. Lucie estuary in Florida in 2016. Now, I'm going to kind of quickly summarize what they did here and show how different parameters come into play here. But we have a full case study of this on our website at seabird.com if you're interested in learning more. But for the most part, at the time of the algal bloom in 2016 in the St. Lucie estuary in Florida, there were huge swaths of highly populated areas were coated in this thick mat of toxic algae. And according to the news, they reported that this harmful algal bloom occurred from nutrient input from a nearby Lake Okeechobee. I'll demonstrate that in a second. They determined that was the cause, nutrients from Lake Okeechobee. Fortunately for us, the Indian River Lagoon Observatory, part of Harbor Branch Oceanographic Institute at Florida Atlantic University, they maintain 5, 6 maybe real-time monitoring sites, each measuring several different physical, chemical, and biological parameters. And these data allowed the scientists to characterize and track different sources of water and actually determine the cause of the harmful algal bloom. These monitoring sites were measuring fluorescent dissolved organic matter, FDOM, sometimes called CDOM, chlorophyll and turbidity, temperature and salinity, nutrients, nitrate and phosphate, and dissolved oxygen. And so with all of these data, the plan was to track and characterize different sources of water to try to determine. So this is just a screenshot I took from Google Maps of the study area. And one thing that I really want to point out here is that something that they do is they have artificial control of freshwater release from Lake Okeechobee. This is here through this canal. My highlighter might not be working. Through this canal into the South Fork of the St. Lucie estuary. This is the St. Lucie estuary where the harmful algal bloom occurred. If we were to zoom in on this Google map, you would see that there are $1 million homes, yacht clubs, houses, golf courses, all sorts of stuff around here, all with a vested human interest and also things contributing to runoff, contributing nutrients, pollution, and then there's lots of recreation going on here. So this harmful algal bloom was a pretty big deal for the people of this area. So this is the location of the monitoring sites in the St. Lucie estuary. So there were 6 stations, 2 in the South Fork in the St. Lucie estuary, this white one here, and this red one here, 1 in the North Fork, this green one here, 1 in the middle estuary, this yellow one here, and then 2 in this coastal area. And so each of these was outfitted with an array of sensors that were really characterizing these different bodies of water. And each one kind of has pretty unique characteristics when it comes to salinity, dissolved organic matter, nutrients, etc. And they were measuring that in real time. So first, we're going to look at salinity and FDOM, or really as a proxy for dissolved organic matter. So looking at salinity and FDOM, again, also referred to as CDOM, they were able to determine the characteristics of 3 primary water masses. Seawater coming from the coast over here, high salinity, low dissolved organic matter. Fresh water released from Lake Okeechobee through that canal that I showed earlier. This has low salinity, medium high dissolved organic matter due to plants, everything. And then runoff entering the estuary. This is low salinity, high dissolved organic matter. These were basically determined by the data from the monitoring systems, knowledge of the release of fresh water from Lake Okeechobee, knowledge of rainfall and everything in the area. And so they had pretty distinct signatures in terms of salinity and FDOM that allowed them to say, okay, this water that we're measuring here came from this part of the estuary. This came from the sea. This came from Lake Okeechobee. During the harmful algal bloom period from June to July, we can see, based on what we know about different masses of water, that the relative input from each water mass is a little bit different from normal. So due to low rainfall at the time, logged by rainfall sensors, meteorological data, there wasn't much runoff. And we could see that by this pretty low dissolved organic matter. Furthermore, at the North Fork and the South Fork, there was minimal seawater penetration. So that tells us that there's not a lot of mixing coming in from the open ocean, this sort of low nutrient seawater. And we also know, based on just the schedules of release from Lake Okeechobee, that there was relatively constant release of fresh water from Lake Okeechobee. So we can see really from this information that most of the input into the St. Lucie estuary is from Lake Okeechobee, not from runoff and not from seawater. We can define that because we have pretty clearly defined our different masses of water based on the salinity and dissolved organic matter characteristics. Next, we want to look at nutrients and dissolved organic matter. And so to start off, we know that this estuary is typically phosphate limited. That's sort of the main nutrient. So we're not really going to look at nitrate in this case. So recall that the hypothesis for the cause of the harmful algal bloom was nutrients from Lake Okeechobee. However, looking at the data from these multi-parameter systems, Lake Okeechobee itself had relatively low phosphate, really hardly more than seawater. If we look at this plot here, in terms of the phosphate concentration, pretty low. Definitely higher when it comes to dissolved organic matter, but it's not as if Lake Okeechobee is contributing huge amounts of phosphate that would trigger a harmful algal bloom necessarily. Most of that nutrient is coming from runoff. So contrary to the hypothesis, freshwater input from Lake Okeechobee was actually dilutive to the nutrient concentration in the estuary. So that gives us a lot of interesting information to chew on. Again, if you want to look at the full analysis, you can read the case study on Seabird.com. But overall, the conclusions that we drew here were that Lake Okeechobee water did not contribute excess nutrients to St. Lucie estuary. reject the hypothesis from the news. That's actually not what's going on. Most of the nutrients here came from the North Fork. That being said, we do have this high discharge of water from Lake Okeechobee, and we also have this evidence that there's low seawater mixing based on the salinity and FDOM plots. So what's going on here? What we really think happened is that due to the discharge of fresh water from Lake Okeechobee, that increased the residence time of fresh water in St. Lucie estuary. So essentially, the freshwater discharge disrupted circulation in the estuary, causing it to become what you might consider to be a high nutrient lake. And so what plants, algae, harmful algal blooms, everything need is high nutrients, sunlight, and enough time to cause a bloom. And that's essentially what happened by the constant release of fresh water from Lake Okeechobee. That caused, we had those high nutrients from runoff, just kind of hanging out in North Fork. We had the long residence time caused by the disrupted circulation from freshwater discharge from Lake Okeechobee. And a lot of that wasn't getting flushed out by seawater mixing. So that resulted in a harmful algal bloom. The observation from the governing body was that regulating the discharge of fresh water from Lake Okeechobee really reduced the frequency and severity of harmful algal bloom events. So pretty interesting stuff here. We wouldn't have been able to determine this without salinity, FDOM, and phosphates. All three of those parameters work together in tandem to provide the answers that we were looking for here. And if we had just salinity, we might see, okay, there's not a lot of seawater mixing in here, but we wouldn't necessarily know why, and we wouldn't necessarily know where this is happening. And we wouldn't necessarily know that Lake Okeechobee was not the contributor of phosphate to the estuary. So by having these three parameters, we could really come up with a much more comprehensive analysis of what happened here in order to provide these answers and then test our hypothesis through observation of discharge from Lake Okeechobee. Now, the instrument that they used on this was not actually the HydroCAT-EP V2, but you could have done a very similar analysis with something like this. So the HydroCAT-EP V2 is our latest multi-parameter moored CTD. This is one of the instruments I refer to as an integrated sensor package. So within this one instrument, we have temperature and conductivity, a pH sensor, a dissolved oxygen sensor, a pressure sensor, and chlorophyll and turbidity. So the HydroCAT-EP is pretty interesting. There's a lot of stuff that it can do. And it's based on the SPE37 moored CTD used widely in research applications around the world. So this is a short video of one that we had deployed off of a dock here in Seattle, Washington. It's currently sampling all 7 parameters near the surface of this location, providing pretty comprehensive monitoring of our study area. It's deployed on this pole. You can deploy it just as you would in SPE37. It's got the same, very similar form factor, and it can really augment sort of studies that you get. And so we had one of these, actually the predecessor, the V1 version, deployed in a estuary in Savannah, Georgia in 2016 when Hurricane Matthew made landfall. The picture on the left shows Florida, not necessarily Georgia, but same hurricane and similar impact. And so this instrument deployed in a tidal estuary showed us some pretty interesting stuff at the time. We were lucky to have this in the water when we did. So from the data on the right, we can see a noticeable drop in temperature and a huge swing in salinity when Matthew passed over the instrument. Prior to that, we really see salinity changing from just the tides as freshwater comes in, seawater comes in, moves out. We see a very regular pattern until the hurricane passes over, when salinity drops significantly and stays pretty unusual for several days after the event. Now, something that is always interesting to me is, had we not known about Hurricane Matthew and I saw this signal in salinity, I would be concerned for my instrument. I would think, okay, maybe at this point, something has damaged my conductivity sensor. Maybe it's filled with sediment. Maybe it has a bubble. Maybe a boat ran into it. So having the context of what's going on is really helpful. On top of that, pH sensors are a little less reliable, at least this kind of pH sensor. They're a little less tried and tested than like conductivity sensor technology. So if I were just looking at pH, I would say, hey, I need to go out there and recalibrate my sensor, potentially replace it, potentially repair it, because this signal that I'm seeing right here in pH really doesn't make a lot of sense. This is not what I expect. Again, assuming I know nothing about the hurricane that's currently passing through. However, because I'm measuring multiple parameters, I can compare that to other pieces of data. So when I plot pH and then I also plot salinity, I'm looking at this and saying, oh, okay, you know, salinity, I trust my conductivity sensor more than I trust my pH sensor. Salinity is seeing a very similar shape. There's something else going on here. So maybe I won't go and calibrate my pH sensor. It seems like something is affecting this that is maybe not damage to my sensor. Something else is going on because I see that in another piece of data. So that gives me confidence that what we're seeing here is actually a natural event, and I wouldn't necessarily have that if I only had a pH sensor in the water. Fortunately, with the HydroCAT-EP, it measures more than just salinity, temperature, and pH. So we can look at a whole bunch of other parameters as the hurricane passed over. And there's a lot of stuff going on here. But of note, we can see a sudden spike in chlorophyll and turbidity as the sediment was dredged up by the hurricane's energy, and presumably photosynthetic biomass increased or maybe became suspended after the hurricane passed. We see that turbidity really picks up and stays, has pretty high variance after the hurricane passed through for several days. On top of that, we see dissolved oxygen rising as the hurricane is approaching, and we see kind of the sudden dip, probably coinciding with the sudden increase in turbidity, and we see our signal in pH. This brings me to another point, is that there's a small gap in data around October 21st, 2016. And so we were looking at this data and we're saying, okay, we're seeing some pretty high turbidity here. I would recommend taking the sensor out of the water, cleaning it and flushing it out. And indeed, we do see this gap in data when they took it out and when they put it back in. Our signal is changing somewhat. So it's possible that we had some sediment caught in our dissolved oxygen sensor, some sediment caught in the plumbing that could be affecting our measurements. And being able to see this turbidity really tells us like, okay, this is a time when it's a good point to go and maintain our instruments, because we know that this signal could be detrimental to our data quality. So that's a really important aspect of having multiple data points, is that not only do you get a more comprehensive scientific picture of what's going on in your environment, you also get some maintenance and quality metrics on your instrument itself, so you can make some decisions on when you need to go out there and service it. Which brings me to my next and favorite point about multi-parameter systems is you can do a lot of really awesome technical troubleshooting with these. I love doing this kind of stuff beyond the scientific applications of related parameters. If you know a thing or two about your sensors, how your sensors work, and what you can expect in different conditions, we can look for clues in each parameter to aid in troubleshooting. So we've got this animated GIF on the right side here, showing this pretty strange problem where we were troubleshooting initially some unusual dissolved oxygen data, as well as salinity data. So by plotting DO, salinity, and pressure together, and then zooming in as we are in this animated GIF, we can see that there is an unusual amount of variance in each parameter that clearly matches the tidal cycle. These kind of up and down signals and pressure are from when the tides are rising and falling. Very, very natural. And while we expect to see some variation to occur along the tidal cycle as different water masses are coming in, the amount of variation we see is really outside of the expectation for this environment. and it is a greater magnitude than we would really expect to see. So that gives us a useful clue, and we can look at various things throughout the rest of the data set. So early on, I can see that salinity is 0 for several days, and I know that if a bubble is caught in the conductivity cell, then salinity is likely to be 0. So that gives me a clue. I didn't necessarily know that from the dissolved oxygen sensor, but knowing what I know about conductivity sensors, I can say there's probably a bubble in there. That's also going to affect your dissolved oxygen data. Furthermore, if there's a bubble in there, that bubble may be larger or smaller depending on the pressure impressed on it, which could cause a greater swing in your dissolved oxygen with the tidal cycle. So I'm looking at this, I'm looking at dissolved oxygen for clues, I'm looking at salinity for clues, I'm pulling up pressure to try to find out, to see if these are matching the tidal cycle. Having all of these parameters tells me a lot more. If I were just looking at dissolved oxygen, I might say, wow, the magnitude of oxygen concentration is changing quite a bit. I don't know why it's got this regular pattern. I don't know if this is real, but having salinity to look at tells me there's something going on with my instrument that needs to be addressed. Having pressure to look at tells me there is a regular pattern that is being influenced by the tides. That's a clue, and that tells me that it could be a bubble, could be sediments, it could be coming out of the water, etc. So there's a lot of information that you can glean from having multiple parameters that you wouldn't have if you just had dissolved oxygen or if you just had salinity. On top of that, with profiling CTDs, in this case, we can see relatively clean data on the downcast. That's dark blue and dark red. But as it's rising on the upcast, we see some squiggly data. It's strange, and it's not immediately clear why this is happening. However, if you look at something like descent rates, you can see that these squiggles in salinity and temperature are pretty much matched with the descent rate of our CTD. And so that's telling me that we don't have flushing through our system. The pump, I know that pump flow through Seabird CTDs is important for optimal data quality. And if our pump is not working, we're going to see our salinity, temperature, dissolved oxygen signal really match the descent rate, the motion of the CTD, as it's forcing data through the plumbing. And so to me, based on what I know about sensors, because I'm measuring descent rate, because I'm measuring salinity and temperature, I can hypothesize that my pump was not turning on during the upcast, possibly also during the downcast. And a subsequent investigation showed that replacing the pump cable eliminated this problem here. So again, plotting several different parameters can tell you some answers that you might not have with just salinity or just temperature. Similarly, I know that both conductivity sensors and oxygen sensors are flow dependent. So if I have a problem with my pump, that's likely to manifest in both parameters. So in a separate CTD profile, I noticed fairly erratic data and some small spikes in salinity, and I suspected it was another pump failure. By plotting dissolved oxygen alongside salinity, I can see the same kind of signal and confirm that, yes, this does seem to be a pump problem. Again, replacing the cable fixed that issue. So once again, having additional parameters gives you more clues into technical troubleshooting to find out why your data are showing what they are. This was particularly helpful when we were testing our prototype ISFET pH sensors. For those of you that are familiar, this is the CFET and the CFOX pH sensors. And so what we know about these is that ISFET sensors respond to chloride ions in seawater. So we need to measure salinity to really account for that and optimize our data quality. Knowing salinity is extremely helpful for optimizing data and understanding if a shift in pH is because of the sensor technology responding to actual changes in pH, or is it because salinity is changing? So in this case, because we are testing prototypes, it's really important for us to measure all of these different parameters to truly characterize our instrument signal. Using the same instruments in estuary with lots of freshwater inputs, we had the same prototype instrument And towards the end of a week-long deployment, we saw that our pH data really started to vary pretty significantly. Because this was a prototype, it was easy to assume that something is wrong with our sensor, looking just at pH. However, we were also measuring salinity and dissolved oxygen with this instrument, data that's coming from more established and field-proven sensors. And so we could see that there's actually something going on in the water. We trust our dissolved oxygen sensor, and we see a similar shape in the dissolved oxygen data. Looking at salinity, we see that it starts to drop. It's more regular at the beginning of deployments. And then we have these low salinity moments. We know that the environment we deployed this in is an estuary where large amounts of fresh water can influence your measurements. And so having the salinity data told us, okay, it rained quite a bit over the last few days. Maybe there was input from rivers, just rainfall, everything. And so this gave us increased confidence that our prototype instrument was working. It was responding to actual changes in the environment. If we just had pH, we would probably pull this one and say, okay, let's figure out what's going on here. Why is this happening? By looking at dissolved oxygen and salinity, we can have more confidence that the instrument's response is more realistic and is more in line with what we expect to see, and gives us confidence that our prototype is working fine. So that really brings me to my conclusion here. More than the sum of its parts, measuring multiple different parameters gives you more than just extra data points to report, extra data points to visualize. These related data can tell a scientific story. As we saw in the St. Lucie estuary, there are related, we can use these to really constrain these biogeochemical cycles. We can look at related data to characterize a mass of water, and we can use that to explain what might be going on. With things like the carbon cycle or nutrient and productivity dynamics, having multiple different instruments that are measuring these chemical, physical, and biological parameters can really explain what's going on in your environment. And then also we can use these things to track and characterize different sources of water. Oceanographers use TS plots. There are BGC tracers like we saw with St. Lucie. And finally, from a technical perspective, data can be related in different ways, like how conductivity sensors and dissolved oxygen sensors are both dependent on flow. We can look at that. If we have a problem with flow, it's going to manifest in conductivity and dissolved oxygen, even if salinity and dissolved oxygen, from a scientific perspective, are not related in our study area. So you can use these features to understand and troubleshoot your systems when your data don't appear to be working as you expect them to be. Okay, with that, we can open it up for the Q&A. I'm going to just open up the chat and take a look.
Great, thank you so much, Greg, for that great presentation. I have some questions. Jules Jaffe submitted something that he was hoping you could cover, asking about, does your CTD work in still water? For example, does water need to flow through the CTD, or is it an induction system?
Yeah, great question. So all Seabird CTDs, or just about all Seabird CTDs, utilize a pump. That's sort of the bread and butter of data quality when it comes to using both a Seabird profiling CTD, where you're moving up and down in the water column, and a moored CTD. With the HydroCAT-EP example, this one is definitely using a pump. Here, let me pull up the, maybe we'll look at the diagram. Okay. So with the HydroCAT-EP here, at this point where we're pointing at temperature and conductivity, this is the intake of the flow path. So we have a pump that is pulling in new water with each sample, and that is flowing past your temperature sensor, your conductivity sensor, your pH sensor, and your dissolved oxygen sensor. And then the exhaust is coming out through this opening right here. That's doing a lot of good stuff. For one, in still water, you're pulling in a new sample to ensure that the temperature, conductivity, pH, dissolved oxygen is actually from a new sample. It's not from water that's been entrained inside of the flow path. On top of that, it is aligning all of these things together. So you can be confident that the temperature, conductivity, pH, and DO that you're measuring is from the same parcel of water because it's sucking in that sample and holding it within the flow path. They're all aligned together, responding to the same thing. With instruments like the 9+ CTD, going all the way up to the top here, this has a pump system that's pulling water through all of the sensors you have connected to it. So again, temperature, conductivity, dissolved oxygen, and maybe something like a transmissometer as well. Some of the Seabird CTDs, like some of the SBE 37s, do not have a pump. You can use them in still water. Your data quality is pretty good, but they do not use an induction type conductivity cell. They have this sort of enclosed electrode glass conductivity cell that prevents any debris, any physical objects from interfering with the electrical field that would otherwise throw off your measurements.
Excellent. Thanks, Greg. Again, everybody, feel free to enter your questions in the Q&A or the chat, and I will moderate. You can also feel free to request to be unmuted, and we can unmute you if you want to ask your question verbally. I do have another submitted question from Andy Nager. He was asking, what are the best practices for how to mount a Seabird FastCat SBE 49?
Okay, sure. So SBE 49, that's really going to depend on your application. The SBE 49 is sort of a small profiling CTD. It's our smallest profiling CTD. It's about the size of an SBE 37, if you're familiar with that, about the size of the, actually I have a diagram right here, the HydroCAT-EP, roughly the same size, about 711 millimeters long. And so you can mount that similarly to how I mounted the HydroCAT-EP in this video we've got here, where you have clamps going around the body of the instrument and holding it to a pole or something. But what I think is important to know is how you are deploying your SBE 49. So some people use these on ROVs and they just kind of strap it to the hull of the ROV. Some people use this on a profiling CTD package, and so they might strap it to one of the bars in the cage. And you might be deploying this. I've worked with people who have deployed these on submarines, so they have just the conductivity cell guard with the temperature sensor and the conductivity sensor just kind of sticking out of the submarine. It really depends on your deployment itself. One thing to note is that the SBE 49 does not have internal memory or batteries, and so it needs to be connected to external power and some kind of data logger. So I would say that the best way we can help you is if you contact tech support at seabird.com. Give us some information about your deployments and some information about how you or what kind of vehicle you intend to attach this to. And then we can really help you with determining how best to mount your FastCat.
Yeah, Greg, Vanessa just actually unmuted me. So we are doing it for an AUV application. And is there any sort of practice in terms of keeping like the pump intake in front of the vehicle, or can you mount it on the bottom, even if it's got vortex shedding off other things?
Yeah, that is a great question that I don't necessarily have an answer to. I can tell you that the intake for the 49 FastCat is it's pretty obvious. It's right on the end of the conductivity cell guard. I really don't know much about AUVs and ROVs, so I don't know how they might be affecting your measurements. What I have been told in the past is that a lot of CTDs on ROVs are not necessarily going to get the highest quality, or let's see, the quality of your CTD profile is not too affected by the motion of the vehicle because it's moving significantly more slowly than say a profiling CTD package that's descending through the water column at 1 meter per second. That being said, I would request that you contact our technical support team about that. We can rope in our science team and really find out what the best practices for mounting that to your specific vehicle would be.
Awesome, thanks.
Excellent. Thanks, Greg. We got a couple more questions that came in. First off, for looking at multiple years, do you have any problems with sensors and drift needling recalibrations?
Sure. So again, that's going to depend on the type of instrument that you are deploying. The HydroCAT-EP, for example, which we're looking at here, the temperature, conductivity, pressure, and dissolved oxygen sensors are the same ones that we use on the SPE37 MicroCat CTD. We rate these to really recalibrating once every year for optimal data quality. But we have published drift specifications that are actually pretty conservative. I can pull up, I think, the data sheets. I don't have that handy, unfortunately. But yes, I would say that every sensor from Seabird, we have very carefully characterized the drift specifications for each sensor. So you know that depending on the accuracy that you need from your instruments, you can calculate how long you might leave it out there before recalibration. For the HydroCAT-EP V2, I will warn you that the pH sensor uses this glass electrode technology that I'd say 99% of all pH sensors utilize. And so that needs to be recalibrated every 90 days in order to maintain the accuracy spec. So that's really the limiting factor of your sensors deployment in terms of data accuracy. So this is the data sheet for the HydroCAT-EP V2. And in this table, we have the typical stability. So conductivity, temperature, pressure, and optical dissolved oxygen. This is identical to the SPE37 CTDs that are out there on moorings, might sit out in the open ocean for 2 years at a time, and still collect high quality data throughout the deployment. That being said, if you look at pH, we have 0.1 pH per 90-day cycle. So depending on if you are looking at getting pH, you might consider something like the CFET or the CFOX. This ISFET pH sensor that we were talking about earlier. I showed the prototype data. That can get a year of data with 0.01 pH accuracy drift over the course of a year, I believe. But yeah, please let me know if that didn't answer your question.
Great, thanks, Greg. And again, if anybody wants to be unmuted, just kind of raise your hand or type in the chat, and I'm happy to unmute for any follow-on questions. We do have another one that came in the Q&A asking, can you filter the tide signal out of the time series data, or does that compound with some of the BGC observations that you make? For example, would an FFT be helpful or detrimental?
Sure, I'm going to need you to define FFT for me, but I will say that for most of the data that I can think of, the tide signal is going to be actually causing changes in your data, as the tides bring in new water. On top of that, so the derived parameters that I showed you here with, you can get from your CTD, let's see, these guys here. The majority of these are taking pressure into account. So density, for example, is a function of temperature, conductivity, and pressure. I guess temperature, salinity, and pressure. And so you want to have the tide signal in there. Changing pressure is actually part of your changing calculation. And so what's really going to happen is if you ignore the tidal signal, say you filter that out, and then you calculate something like density or sound velocity, what's going to happen is these are already accounting for pressure. If you're taking pressure out of that and just using static value or filtering it out, then your data is actually going to be less accurate than if you had kept it in there. let me know if I didn't understand the question, and I can elaborate on that.
Great, thank you, Greg. I don't see anybody reaching out to be unmuted, so I think you probably answered it. Don't see any other questions coming in. I do have one other pre-submitted question. They were asking, how does Seabird CTD data compare to satellite data?
Okay, that's a super interesting question. So what I know about satellite data is that it needs to be ground truthed, and I sort of think of it as more quantity over quality, and as technology gets better, that quality gets better. Satellite data is looking at things like maybe sea surface temperature, chlorophyll in surface waters, and there's a lot of interesting stuff being done with radiometers. I would say that a sensor in the water is always going to be superior than a remote measurement from satellite. And what we do with most of these things is we ground truth our satellites. So there are several kind of like long-term monitoring stations, like HOTS in Hawaii, where we're measuring these parameters, we're ground truthing our satellite data. And so that's acting as almost like a calibration for the satellite, where say your satellite is beaming down, looking at Earth, looking at the ocean, measuring, I don't know, irradiance or something. It's important to have a radiometer in the water telling us, okay, our satellite is telling us this raw data based on the calibration we've done. This is telling us that our irradiance is this. How does that compare to a sensor that's actually there in the water, measuring the same thing? And do we need to recalibrate our satellite? Do we need to change our algorithm for converting raw satellite data to irradiance? So again, sensor in the water is pretty much always going to be superior in terms of accuracy than a remote sensing device.
Excellent. Thanks, Greg. Well, I don't see any other questions coming in, so unless something pops in the next few minutes. But I wanted to thank you for this excellent presentation, very great discussion. I appreciate it. And again, if anybody has any follow-on questions, feel free to reach out to myself. We can facilitate that. And with that, it doesn't look like we have any more questions coming in. So I will just briefly mention that we have our next Scripps Technical Forum coming up February 25th. And we'll be hearing from Matt Moldovan with Suburban Marine. And he's going to be talking about his new Opal Eye technology, which is his new open source smart ocean camera. So thank you all again for joining us today. Again, if you have any ideas or suggestions for presentations or companies you'd like to hear from, please let us know. And I wish you all a very happy weekend. And thanks again, Greg.
Yeah, thanks, Vanessa. Thanks for attending, everybody.
Have a good weekend, everyone.